Calculating volume of combined solids, additive approach. Welcome, everyone. To begin today's lesson, let's take a look at our first slide. In our previous subsection, we established the principle of additive volume, which essentially tells us that volumes can be added together. In this tutorial, we are going to move beyond the theory and focus on the practical application of this principle. You'll notice that most real-world objects aren't just simple, single geometric shapes. Instead, they are what we call combined solids, which are formed by joining two or more basic solids together. To find the total volume of such a complex object, we are going to use a specific, systematic process called decomposition. We will explore exactly how to perform this decomposition in the upcoming slides. The process of decomposition. Now that we've established the principle that volumes can be added together, let's talk about how we actually approach a complex shape. We use a technique called decomposition. Think of decomposition as the act of breaking down a complex, three-dimensional object into much simpler, recognizable geometric shapes. Shapes like cylinders, cones, or spheres, whose volume formulas we already know and have mastered. To make sure we don't get lost in the complexity, I want you to follow a systematic, step-by-step process. In the next few slides, we are going to walk through each of these steps together, starting with how to visually analyze the object. Step 1. Visual analysis. Now that we understand the concept of decomposition from the previous slide, let's look at how to actually begin this process. Step 1 is visual analysis. Before you pick up your pencil to do any math, you need to carefully observe the object in front of you. Your goal here is to mentally strip away the complexity and identify the basic, simple solids that make up the whole. To help you do this, I want you to practice asking yourself specific questions. For instance, you might look at a shape and ask, does this look like a cylinder with a cone on top? Or perhaps, is this a cuboid with a hemisphere attached to its side? By asking these questions, you are setting the stage for the next step, where we will formally list these individual shapes. Step 2. Identification of constituent solids. Now that you have performed your visual analysis in the previous step, it is time to move to Step 2, which is the identification of constituent solids. In this stage, you need to clearly list out each individual shape you identified during your analysis. To make this concrete, let's look at the example of a capsule. If you look at a standard medicinal capsule, you will see it isn't just one single shape. Rather, it is composed of a central cylinder with a hemisphere attached to each end, so a cylinder and two hemispheres. By listing them out clearly like this, you create a roadmap for the next steps, where we will extract the dimensions and apply our formulas. Step 3. Extracting dimensions. Now that we have identified our individual shapes in the previous step, we move on to Step 3, which is extracting dimensions. This is a crucial part of the process where we hunt for the specific measurements needed to plug into our formulas. You'll need to look closely at each shape to find values such as the radius, represented by the letter R, the height, represented by the letter H, or, for rectangular shapes, the length, breadth, and width, which we denote as L, B, and W. As you're scanning the object, keep a sharp eye out for a very important detail. Often, different parts of a combined solid share the exact same dimension. For instance, if you have a cone sitting perfectly on top of a cylinder, the radius of the cone and the radius of the cylinder are usually the same. Recognizing these shared measurements early on will save you a lot of time and prevent errors in the steps to follow. Step 4. Applying individual volume formulas. Now that we have identified our shapes and extracted all the necessary dimensions in the previous steps, we move to Step 4. This is where the actual calculation happens. You are going to calculate the volume of each constituent solid separately, using the standard formulas you've already learned. Let's quickly review them so you have them fresh in your mind. First, for a cuboid, the volume is length times breadth times height. Next, for a cylinder, the volume is pi times the radius squared, times the height. If you are dealing with a cone, remember that it is exactly 1/3 of a cylinder with the same dimensions, so the formula is 1/3 pi times the radius squared times the height. For a full sphere, the formula is 4/3 pi times the radius cubed. And if you have a hemisphere, which is just half of a sphere, the formula is 2/3 pi times the radius cubed. Keep these formulas handy, because in the next step, we will be bringing all these individual results together to find our final answer. Step 5. Summation. Now that we have calculated the volumes of each individual shape separately, we reach the final and most crucial step, Step 5, which is summation. To find the total volume of the entire combined object, all you need to do is add the volumes of all the individual parts together. Mathematically, we express this as total volume equals V sub 1 plus V sub 2, and so on up to V sub n. Essentially, by summing up these separate components, we arrive at the complete volume for the entire complex solid. Real-world example, the grain silo. Now that we have mastered the 5-step process of decomposition, let's put it into practice with a real-world application. Imagine a farmer who needs to know the capacity of his grain silo. Looking at the structure, we can see it isn't just one single shape, but a combination of two. The main body of the silo is a cylinder, and sitting directly on top of it is a conical roof. To solve this, we have been given some specific measurements. First, the radius for both the cylinder and the cone is 3 meters. Next, we have the heights to consider. The height of the cylindrical part is 10 meters, while the height of the conical roof is 4 meters. Our objective is to find the total volume of this entire silo. As we move to the next few slides, we will apply the steps we just learned to find the solution step by step. Step-by-step solution. Now that we have our scenario, let's move into the solution phase. Following the systematic process we discussed earlier, our very first step is step 1, identify the constituent solids. Looking closely at the description of the grain silo, we need to break this complex object down into simpler shapes. By analyzing the structure, we can see that the silo is composed of exactly 2 parts. First, a cylinder forming the main body, and second, a cone acting as the roof. List the given dimensions. Now that we have identified our 2 shapes, the cylinder and the cone, let's move on to the next crucial step, which is extracting our dimensions. Looking at the problem description, we can clearly see the measurements we need to work with. First, notice that we have a common radius, which we will call r, and it is equal to 3 meters. This is a very important detail because it means the base of our cone and the base of our cylinder are identical. Next, we have the height of the cylindrical part, which we'll label as h sub 1, and that is 10 meters. Finally, we have the height of the conical roof, which we'll call h sub 2, measuring 4 meters. Keep these values in mind, as we are about to use them in the next step to calculate the volume of each part separately. Calculate the volume of the cylindrical part, V1. Now that we have identified our 2 shapes and listed their specific dimensions on the previous slide, let's move on to the actual calculation. We will start with the first part of our silo, which is the cylindrical main body. To find its volume, we will use the standard formula for the volume of a cylinder, which is pi times the radius squared, multiplied by the height. Looking at our given values, we substitute the radius of 3 meters and the height of 10 meters into the formula. This gives us pi times 3 squared times 10. Squaring the 3 gives us 9, and when we multiply that by our height of 10, we get a volume of 90 pi cubic meters. We'll keep it in terms of pi for now to maintain precision, and we will use this value in our final step. Calculate the volume of the conical part, V2. Now that we have successfully calculated the volume for the cylindrical base, let's move on to the second part of our silo, the conical roof. To find the volume of this conical part, which we'll call V2, we will use the standard formula for the volume of a cone, which is 1/3 pi times the radius squared times the height. Looking at our dimensions from the previous slides, we know the radius is 3 meters and the height of this specific conical section is 4 meters. So, let's plug those values into our formula. We start with 1/3 times pi, multiplied by the radius of 3 meters squared, all multiplied by the height of 4 meters. When we square the radius of 3, we get 9. This simplifies our equation to 1/3 times pi times 9 times 4. To make the mental math easier, notice that 1/3 of 9 is simply 3. This leaves us with 3 times pi times 4. Finally, multiplying 3 by 4, we arrive at our result. The volume of the conical part, V2, is exactly 12 pi cubic meters. Keep this value in mind, because in the next slide, we will add this to our previous result to find the total volume of the entire silo. Calculate the total volume, V total $. Now that we have calculated the volumes of our two individual parts separately, the cylinder and the cone, we reach the final and most crucial step, summation. To find the total volume of the grain silo, we simply apply the principle we discussed earlier by adding the two volumes together. So, V total equals V1 plus V2. Substituting our specific results from the previous slides, we have 90 pi plus 12 pi. When we combine these like terms, we get a total volume of 102 pi cubic meters. Now, if you are working on an exam and the question asks for a decimal approximation, you can substitute pi with 3.14. Multiplying 102 by 3.14 gives us a final approximate volume of 320.28 cubic meters. This completes our calculation, but before we move on, I want you to pay close attention to the next slide, as I'll be highlighting some very common pitfalls that students encounter when working with these types of problems. Common mistakes to avoid. First, a very important distinction. Do not confuse surface area with volume. When we calculate surface area, we often have to subtract the joining faces because those surfaces are no longer on the outside. However, when we are calculating volume, as we saw with our grain silo example, volume is always additive. You do not subtract the area where two shapes touch, because that space is still filled with material. It is still part of the object's total capacity. Second, be very careful with height identification. This is a tricky one. In many problems, the question might give you the total height of the entire combined object. You must be careful to distinguish that total height from the individual height of each component. For instance, if you are given the total height of a capsule, you might need to subtract the radius of the hemispheres to find the actual height of the cylindrical middle section. Always double-check which height you are looking at. Third, watch out for formula errors. It sounds simple, but it is incredibly easy to get caught up in the calculation and forget a crucial fraction. Specifically, remember to include the 1/3 factor when calculating the volume of a cone and the 2/3 factor when dealing with a hemisphere. Forgetting these small constants will lead to a significantly incorrect answer. Finally, always check for unit inconsistency. Before you start plugging numbers into your formulas, ensure that every single dimension is in the same unit. If one measurement is in centimeters and another is in meters, your final result will be incorrect. Always convert them to a common unit first. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the principle of adding volumes, there are a few traps that students frequently fall into, so please pay close attention here. If you can avoid these 4 mistakes, you will be well on your way to mastering these types of problems. Key takeaways. First and foremost, remember that decomposition is your primary strategy. Whenever you encounter a complex, unfamiliar shape, don't feel overwhelmed. Your goal is simply to break it down into simpler, recognizable pieces. Second, keep the principle of additive volume in mind. The total volume of any combined solid is simply the algebraic sum of the volumes of its individual parts. As we saw in our grain silo example, you just find the volume of each piece and add them together. Third, always keep an eye out for shared dimensions. In many problems, you'll notice that a cylinder and a cone might share the exact same radius. Identifying these shared values early on will significantly simplify your calculations and prevent errors. Finally, I want you to follow this systematic order of operations. First, identify the shapes. Second, extract the necessary dimensions. Third, calculate the volumes of each part individually. And lastly, sum them all up to find your final answer. If you stick to this step-by-step approach, you'll find even the most complex solids become much easier to manage. To wrap up our lesson today, let's review the key takeaways to ensure you have a solid foundation for your upcoming practice problems. That concludes our tutorial. Great job following along.